Hello again. In this mini lecture, we are going to talk about yet another property of stars called their spectral types. And this is covered somewhat in section 17.3, but some of the material here is, especially the history I'm going to tell you, is not in the book. The story of spectral types begins back in the late 1800s and early 1900s. Harvard College Observatory received a large sum of money to start to take pictures of all the stars in the sky. This money came from the Draper family. The Draper families were early photograph pioneers into daguerreotypes, and they made some of the first astrophotos of the sky. So they wanted their money to go to taking pictures of stars, and Harvard College got that money. So what Harvard decided to do was take spectra of all the stars, because as we learned back in chapters 3 and 4, spectroscopy can tell us lots of things about objects, such as if it's moving or not. And so a large project was begun where Harvard astronomers went to several telescopes in both North and South America, and they took spectra of hundreds of thousands of stars and shipped those spectra back to Harvard. Now at Harvard there was a group of people assigned to sort and classify the spectra of stars. They were known as the computers. There were no electronic computers of the day, so they were doing by hand computing. And most of them, well in fact all of them, were male. The head of Harvard College Observatory, Edward Pickering, he's the one man in this photo. He was not happy with how well the computers were doing, and one day Pickering yelled at a male computer who wasn't working very hard and said, "My maid could do better than you." And so he fired the guy and went out and hired his maid. Now, Pickering knew what he was doing. He wasn't just picking any random person. He picked a very smart woman to fill the shoes. He had to sell this idea to the other astronomers at Harvard, who were all male, and he did it by telling them that women work for less money. That instead of paying 50 cents an hour, which is what they paid the males, they only had to pay the women 25 cents an hour. So they could have a lot more people working and process these data much more quickly. Pickering was, though he was a women's right advocate of the day. He was a suffragist. He wanted women to have the right to vote. He wished that they would be able to get degrees at universities, but he was limited in what he could do, and so this was one of his ways of contributing to that movement. The women who he hired became known as Pickering's harem, obviously a little derogatorily, but there was never any sexual relationships between Pickering and these women. They were just working for him. The housekeeper that Pickering hired was Williamina Fleming, pictured here on the left. She was trained as a teacher. She was trained in science. She was Scottish, had gotten all this training over in Scotland, and had married a Scotsman who brought her over to the United States. They settled here. She got pregnant, and then her husband left her for another woman. And to be a single pregnant mom in those days was not well looked upon, even though it wasn't her fault. It didn't matter. She was looked down upon by society, and that's why she couldn't get a teaching job, so she took up housekeeping as an occupation. But Pickering took pity on her, hired her, first as his housekeeper and then as the first female computer. And she was put in charge of figuring out how to sort all of these spectra that were coming in. When she looked at the spectra, she noticed that almost all the stars had hydrogen lines, in the spectrum, but some of the spectra had stronger hydrogen lines than others. And so she decided to classify the stars based on how strong hydrogen appeared in the spectra. And the stars that had the strongest hydrogen she labeled A. Those which had almost as strong hydrogen she called B, and she used letters of the alphabet all the way down to P and Q. So P's and Q's had very weak hydrogen or almost no hydrogen visible. A's and B's had really strong hydrogen. And that was a very useful system, and it allowed them to classify the stars very quickly, and they started separating them out. Fleming then became in charge of hiring other women computers. One of the women she hired was Henrietta Swan Leavitt. Henrietta Swan Leavitt was another woman who wanted to do astronomical research, but that was not allowed by Harvard College. So she joined the computers, and she was more interested in variable stars than spectroscopy. So she worked on classifying how bright stars were. There are some stars that change their brightness over time. And Leavitt realized that there were a handful of stars, a certain type of variable star, that changed their brightness very regularly. And these are nowadays called Cepheid stars, after Delta Cepheid, the first one of these to be recognized. And their brightness changes very regularly, so they go from faint to bright on a regular schedule, almost like clockwork. And what Leavitt realized was that the more luminous Cepheid stars, those that were putting out more energy, took longer to complete one brightness cycle than the less luminous ones. And in fact, if you could measure exactly how long it took a star to do one cycle, then you could determine what its luminosity is, what its energy output is. And then she also realized that if you could see, since you knew how luminous the star was, you could go out and measure how bright it appeared, and that allows you to get the distances to the stars. And we'll see in our next couple chapters from now that these stars are very useful to finding distances to galaxies, because we can see them in other galaxies and that are far too far away to ever hope to do parallax work. So this relationship became known as the Leavitt law, and it's still used quite a bit today. So Leavitt worked on variable stars. Another woman who was hired was Annie Jump Cannon. That's her real name. She was a very intelligent lady, and she suffered from, I believe it was scarlet fever, and her bout with scarlet fever left her mostly deaf, so she couldn't hear very well. But she got the hang of classifying stars very quickly. But over her time at Harvard College Observatory, she classified by hand, by eye, 300,000 stars all by herself, which is just a tremendous amount of work. And you think about how much time that would take. If you only spent 1 second with a star, that would take you 100 hours, but of course it would take, to do this properly, would take minutes upon minutes. So she was very fast, very productive. She also came to realize that the sequence that Fleming came up with, the letters from A to Q, was a little too complex, and it didn't reflect reality. Cannon noticed that the blue stars, some of the blue stars had O letters, some of them had B letters, and some of the red stars had M's and some had G's, and so she began to realize that the temperature of the star was related to the spectral letter they were getting. So she reorganized the spectral sequence by temperature of the star. She also simplified it and got rid of most of the letters, went from all the letters from A to P to 7 letters, and we'll see those in 2 pages. So Annie Jump Cannon reorganized the stellar sequence so that these letters that were being assigned to them meant that they were classifying the temperature of the star. The last of Pickering's theorem we'll talk about was Cecilia Payne-Gaposchkin, who she, again, had studied in England. She got a PhD in astronomy. She married a Russian gentleman, which is why her last name went to Gaposchkin. They moved to the United States, and at first Gaposchkin was not allowed to work as a professor at Harvard College Observatory, but she was younger than most of the other women, and she lasted long enough that she was finally hired as a professor at Harvard in astronomy. Was the first female professor there. She was also extraordinarily intelligent, and she was able to work out the physics of the stars, why stars of different temperatures had different spectra, why the hydrogen lines were different at different temperatures, and she was able to use that to determine what all stars are made out of. And she discovered that stars are not made out of the same material as the Earth, that stars are mostly made out of hydrogen and helium, as we learned about in our chapter on the Sun. Cecilia Payne-Gaposchkin was the first person to figure that out. So here's a summary of the contributions, what you may want to know for homeworks or exams. Pickering was the director of the observatory who hired educated women to work as computers at the observatory. First woman he hired was Williamina Fleming. She was the first female computer and supervised later hires, and she was the one who developed this spectral sequence based on how strong hydrogen lines were, lettered from A to Q, with A being the strongest lines and Q being the weakest ones. Henrietta Leavitt discovered that relationship between variable stars and their luminosity, between a specific type of variable star and their luminosity, and we can use that to get distances to these variable stars. Annie Jump Cannon classified well over 300,000 stars, and she revised and simplified the spectral sequence to the form that we use today that's based on temperature. And Cecilia Panga-Pashkin determined that the differences between the spectra is primarily because of temperature, not because of their composition, and she found that almost all stars have very similar compositions: 75% hydrogen, 23% helium, and 2% heavier atoms. So the spectral sequence we use today, this is the one that was simplified and rearranged by Annie Jump Cannon, is OBAFGKM. And one way that astronomers remember that is "Oh, be a fine girl," or "Oh, be a fine guy, kiss me." Turns out these letters aren't enough, that within each letter there's a range of temperatures. So we since have added a number after the letter to indicate subdivisions, with the number 0 being the hottest and 9 being the coolest. So the Sun is a G2 star, which means that it would fit into the G classification. So it's sort of in the middle of this spectral sequence. And the 2 means that it's toward the hotter end of all the G stars. So here are some examples of in a table of the spectral classes and their approximate temperatures and what lines are there. I don't ask you to memorize this. The main thing to remember is the order, OBAFGKM, and also that the A's have the strongest lines. And notice that the A's are in the middle of the sequence. They have the strongest hydrogen lines. They're about 10,000 degrees, but they're not the hottest stars. There are hotter stars, and the hotter stars have weaker lines. They go to B, and then the hottest ones, the O's, have very weak hydrogen. Then you go to cooler stars, FGKM, and since those letters are higher or later in the alphabet, we know that they have weaker hydrogen lines as well. And so we want to know, why does the strongest hydrogen come in the middle at a middle temperature? Here is just an example, a picture of several stars of different spectral types. And up at the top, I indicate which element is indicated by different lines. The little Greek letters next to the H's indicate those are hydrogen, and we call the longest wavelength hydrogen line alpha, the second longest wavelength beta, and so forth. The HEs, those are actually helium lines. And down underneath we indicate a few more. TiO is a molecule called titanium oxide, and sodium is the same sodium as in salt. And if you look at this closely, what you can see is that the hydrogen lines, let's pick here at H beta, they're strongest here at the A stars, as we would hope. They get weaker as you go into B stars and into O stars, and they get weaker as you go into F, G, K. They almost completely disappear in the M. They're still there, you just can't see them on the scale. Notice that other lines work slightly differently. Let's look at helium. Helium is here. Now you have to be careful because sodium is close to it. Helium is to the left of sodium. And you notice that helium is strong in the O and the B stars, and then it fades away and we don't see it again. Sodium is strongest in the coolest stars and then gets weaker as you go to hotter and hotter stars. So different lines behave differently over temperature. So why would the spectral lines change with temperature? Let's talk in terms of hydrogen right now. And remember that light and the atoms are related, that if we have an electron in an atom and it drops in energy level, it has to get rid of energy, and it does that by releasing light, and that light comes out at a very specific wavelength. These are the emission lines that we talked about back in chapter 4. For hydrogen lines, the optical light, those that we can see in the spectra on the previous page, come from electrons dropping to the second energy level, this first excited state, so second energy level. Ground state is down here. So electrons are at higher levels and they drop down, or they're at this second level and they move up due to absorption. The longest wavelength going from the third energy state to the second one, that releases red light, and then from this energy state down to the second is aqua, this one is blue, and further other ones go into the violet. So if a star is cool, like the M stars, almost all the hydrogen atoms have the electron in the ground state. There's not energetic enough to get that electron out of the ground state. It takes ultraviolet radiation to get the electron out of the ground state. There's no ultraviolet radiation in something that's 3,000 degrees, so the electrons sit there, which means that to get these lines in the optical, we need the electron to be moving around the second and third energy levels up here. The electron's not there, so it can't make any transition, so we don't see any lines. That's why M stars and K stars have very weak hydrogen lines. In a really hot star, once you get up above 15,000 to 20,000 degrees, they're so hot that there's lots of ultraviolet light around and lots of energy, and so the electrons just get completely removed from the atom altogether. They fly off, they're flying around on their own, they don't sink back into a hydrogen atom, and so now the atom has no electron to go through these energy levels, which means that you won't get the lines. This is why O stars have very weak hydrogen lines, because almost all the hydrogen in O stars is ionized. They have no electrons to do these transitions, so you can't see them. A stars are where you have the most electrons up in that second state to move around and make the most transitions, which is why you see this line strongest there. So again, as you get hotter, as you go from A to B to O, the electrons leave the atom altogether. They aren't there to make the line. As you go to cooler stars, F, G, K, and M, there are fewer and fewer hydrogen atoms that have this, that have the electron up in the state where it needs to be to make these lines. The same basic principles apply for all these other lines in the spectrum as well. You see here in the G star, there are lots of lines that aren't there in the hotter stars. These tend to be from metals like iron, and you get iron too hot and the electrons leave. Sodium is really strong at cool, but you make it too hot, its electron leaves. Helium has two electrons that sit in the ground state until you get them very hot. So that's why we don't see the helium line until you get up into the O and the B stars. So the differences in stellar spectra are due to their temperatures of the stars. Different atoms react differently, and by knowing how these atoms react to temperature, you can calculate both what the temperature of the star is and how common that element is in the star. This is what Cecilia Payne-Gaposchkin did. This is how she found out that all of these stars, despite the fact that they have very different looks, are mostly made out of hydrogen and helium. This completes the mini lecture on the stellar spectral sequence, and you can now go on and complete the response to mini lecture 3.